Hello, Ken.
Hey.
How are you?
I'm good. How are you doing? You doing good this morning?
Yes, it is going fine as of now.
Oops.
Oh, is that an alarm that you went?
Yeah, sorry about that.
Okay. Everything okay?
Yes, yeah, everything's okay. Thank you.
The weather cannot be more severe on your side than me, right? I probably is in the same region as well. The weather is
Yeah.
okay. So here is a few things I wanted to talk about the exam and other things. Let's see. I think I did. Okay, so the point I have is, so we were, the plan was to have a midterm exam on April 6th, right? Which was a Tuesday. It's about a little after 1 week from today. Let's say 2 weeks from today. But here is my proposal, since we are a little behind, and if I were to work around this exam, I'll get a class, correct? So here is my proposition. There is a homework 8 I have already posted, and I suggest that we make it due on, let's say, March 30th. I think March 30th is a Tuesday, or Tuesday or Thursday, let's say. And homework 9, which is like this, is on Hamilton. And this is on the action principles. So let's say conserved quantities. And I suggest that this you make due on Thursday. Like I'll be able to finish this by next Tuesday. Okay. And after that, my plan was that, okay, I stop here and then I'll switch over Kepler problem. And I was thinking of skipping what is called Lagrangian multipliers. But instead, it strikes me that I can do Lagrangian multipliers as another homework, and I'll cover that in the lecture for midterm. So there will be homework 10, which will be basically 8. This will be due on after this April 8th, and this will be on Lagrangian multipliers. And the proposition here is that this will be counted as midterm 2. So these two are connected. So homework 10 will be treat it as midterm 2. Homework 10 or these three homeworks together, some weightage of these three together will be midterm 2. So no official midterm 2. I'll use the homeworks to assess midterm 2. Is that any comments on that?
No comments. I like that. It's fine.
Because it's just one or two students, and since I see that both of you guys are doing your homework on your own, so that itself is an assessment as far as I'm concerned. There is this part that when there is an exam, you tend to study the whole material together, you summarize it and so on, which is what you will miss. You see what I'm saying?
Yes.
But I think it's not as major a problem as that we cannot give it up, kind of. Okay. So
Okay. Yeah.
So these two have been uploaded. And I'll upload homework 10. Okay.
Okay. Sounds good.
Okay. So this is again stationary action principle. And including the variation at the boundaries. So I was trying to summarize it last time, and then I went ahead and started doing what is Hamiltonian. But let's start right away here. So we have an action which depends on the path of a particle. And this should be a vector principle. Should I write this as a vector? Yeah, let me write this as a vector so that there's no. No, let's keep it one-dimensional. It will be, there will be more clarity. The generalization is almost trivial. So let's not get distracted by vector feature of this. Let me write this down. We have the two limits as T1 and T2, that's the boundary of the time dependence in the position of the particle. And the Lagrangian depends on x, which is a function of time, derivative, which is velocity of the position, and it could have explicit time dependence. That's a general action, and we said this is the Lagrangian, that's the action. I should point out here a few things. This time dependence in x here, which appears at 2 points, this is implicit. I show this explicitly here so that we know where the time dependence is, but that particular time dependence is implicit in the sense that if I have to see the change in time here, I'd first differentiate the Lagrangian with respect to x, and then x dependence or things like this, an indirect dependence. But these two dependences, this time here and this time here, that's explicit. Which means that whenever I make some variation, especially this is a dummy variable t, that is the explicit variations that comes in. So that plays a role in the discussion that we are going to have very soon. So that differentiation is important. Okay, we have been talking about make a change in the action and look for what is the change on the right hand side. And we say that stationary action principle says that this change should be 0. But now we have two more variations, right? We can actually think of varying T1 and T2 also. So let's do the complete variation. That's a goal. Right? So, so I would like to do W plus a change in action. What are the changes we make? We make in both X and maybe write that explicitly here. So I'm going to make the change in X, going to X. Let's say this is X as a function of time. This is X as a function of time plus an arbitrary variation, arbitrary function you add, which is infinitely small. That's one thing we talk about. And then we have the boundary. This is T1 plus T2, delta T2, T1. Notice this is all along the path. This variation is a functional variation. Here, T1, if you want, is just the boundary. And we also say T2 is changed from T2 plus T2. And we would like to know what is the change in the action due to this arbitrary variations. So we do this algebraically. So change will be W plus delta W. Because of these three variations, there is a change in the action. And that will be given by, just explicitly write this down. Replace T1 plus delta T1, T2 plus delta T2. Notice time doesn't change, right? That's a dummy variable. The integral type T variable in T, that doesn't change at all. And the Lagrangian changes except for the X, right? There is no change in time. So this is X plus delta X. Notice there is a time dependence here, but I'm not showing it just for avoiding the clutter if you want. And there is d by dt of again X plus delta X. And T, right? There is no change in T. Right? T is a dummy variable. That's a complete change if you want, and we would like to get this change in the action. So we want to isolate whatever was there before and move it, collect all the terms with delta X and delta T1 and delta T2. Okay. So how do we proceed in this? Notice that the variation in time is in the limits. That's not a convenient place for it to be there or to do algebra with that. So we would like to bring this delta T1 and delta T2 inside. And how do we do that? This is an integral, so I'll make a substitution. So let's make a suitable substitution. And the substitution we make is the following. So let T prime be equal to T minus delta T. And this is an arbitrary function. And let me call that to be a function of T. But with the restriction that, so this is a completely arbitrary substitution, except that I require that plus, and I require that this substitution has the value at T1 to be exactly delta T1. Right? This is a very special delta T1 here. Like it's arbitrary, but it's that is what you're actually dealing with. But we say that whatever substitution we make, that condition. And let me also say delta T at T2 is equal to delta T2. Is that clear? Any questions at this stage?
No questions. No, thank you.
So the idea is, if this is the substitution, put it back in there, rewrite the whole Lagrangian in terms of T prime instead of T. So we have W plus change and action, right, is equal to, what are the limits? Let me actually go slowly, right? So let me do all these changes separately. What is the limit T2 plus delta T2? So T2 plus delta T2, that's the upper limit. That will be equal to, this is in T prime, right? So what happens to T2 plus delta 2 when I substitute it in here? So that's T2. So this goes to, if you want. Or maybe let's say, how do I say this? When I substitute, or yeah, how do I say this? At T is equal to T2 plus delta T2, at this, or when T is equal to so much, T prime is equal to T2 plus delta T2 minus delta T of T2. But delta T of T2 is delta T2, so that's T2 itself. So that's the upper limit, if you want. For the lower limit, when T is equal to T1 plus delta T1, that's the lower limit. T prime is equal to T1 plus delta T1 minus delta T. So the limits become very simple, right? T1 and T2 when we make this substitution. That's the idea. We chose our substitution to be. We want to write dt in terms of dt prime. So let me, for that purpose, let me rewrite this as t is equal to t prime plus delta t of t. Substitute this again. So I get, so this is equal to t prime plus delta t of, substitute this again. So this is like iterating it. There's another delta t. But the contribution due to this delta t inside here is going to be second order. That's the same as t prime plus delta t as a function of t prime, which is primarily saying that whenever there is a small quantity variation in function, whether it is t or t prime, it doesn't matter. Right? The change in going from t to t prime doesn't give, it's a higher order effect. Any questions there? How I manipulated that?
Not right now. No, thank you.
So if that is the case, I want dt here. So dt would be equal to dt prime plus dt prime d by dt prime of delta t, function of time t prime. So I have dt is equal to dt prime 1 plus d by dt prime of delta t. I have not written the t prime dependence, it's understood that that's a t prime dependence. And so that's our substitute. So dt inside this integral has to be replaced with dt prime. So the goal is to, I want to write everything in terms of dt prime, right? So that's good. So I have done that. There's also this derivative term showing up here. Right? That is this derivative with t. I want to be able to write that also in terms of t prime. So let's work on that. So let's and then I can write the integral. So I go back to my t prime expression. So this was t prime is equal, maybe a little bit to the left, more space. So t prime is equal to t minus delta t, function of t. I'm interested in d by dt going into d by dt prime. So this is the same as dt prime over dt times d by dt prime. Just chain rule. But this is equal to, I can take the differentiation there. That will be equal to take the derivative. So that's 1. Take the derivative of this with respect to dt. So that's d by dt of delta t of t. But the goal is to write everything in terms of t prime. So I should be able to get this also in terms of t prime. Again, use a chain rule. That's equal to 1 minus dt prime over dt times d by dt prime. And of course, this is having t prime dependence in here. I can replace t prime and t whenever I want to. Times d by dt. d by dt prime again put in there, but that's a higher order term. So this is, if you want, this is 1 minus d by dt prime of delta t times d by dt prime. Notice that I should again replace this dt by dt prime by dt with 1 minus derivative with respect to t, but that will be a second order. The second term in that will be second order because there will be two variations. So that's your 3 quantities that you need, basically 2. What is the differential dt in terms of dt prime, and what's the derivative of t with when you write it in terms of t prime. With those 2 in, I can now write the Lagrangian, and let me go to the other board because I have more space. So my change in the action due to these quantities will be, the lower limit is simply t1 now, and the upper limit is just t2 as we showed. That's the simplification. dt is in terms of dt prime. This is dt prime times 1 plus and the Lagrangian now, which is the Lagrangian, which is a function of x plus dx. X plus dx, and this is derivative of x with respect to t, which is the same as 1 minus d by dt prime delta t and then there is dx by dt prime. And the second variation is d by, that is plus, right? Plus d by dt. So that's just simply d by dt prime of delta x, which is a function of t. Again, here I have made So there should be two terms here, but the second one is second order. Maybe I should write that down and then I'll cut it out. So this is 1 minus d by dt prime delta t times d by dt prime of delta x. Notice one can multiply this, or the second one can multiply this. The second one is second order. So basically, I can strike this out. All this is in the dependence, right? Lagrangian is a function of this plus this. So there are three terms in that second dependence. And eventually there is t here, but t gets replaced with t prime plus delta t. Is that visible? Maybe move it a little bit up. Okay, so let me rewrite this a little bit. Once and
Suggest
Lagrangian.
that x is because of higher order terms. That's what you said?
Yes, because notice these two terms, there is a variation in delta t and variation in delta x. That's two variations, right? That's higher order.
Okay,
So
thank you.
Good. So this is x plus delta x. And let me write this out clearly. So the 1 multiplied this is the actual derivative, this time in terms of t prime. Then there is minus of dx by dt prime. Let me write that in the front. So it's dx by dt prime and d by dt prime of delta t. And the third one is minus of d by dt prime delta x. Maybe this can be written first because this shows the variation in x right away. Maybe let me rewrite this first. Let me write this plus d by dt prime delta x, and then there's this minus of dx by dt prime delta t, and t prime plus delta t. Let's pause for a moment and see what are the new variations. If we had just made the variation in x, I would have got this term. I would have got this term. That's it, right? I wouldn't have got this term because this is a variation in the time or the boundary. So first we made the changes in the boundary, and then very nicely, if you want, we transformed the variations in the boundary into the Lagrangian. And the changes that are coming in is here, here, and here. The three places where the time change in the boundary shows up. Is that clear?
I believe so, yes. Thank you.
Okay, so now we expand this out. That's what we do typically, right? We start with the Lagrangian, Taylor expand this, and all these are the changes, right? Expand it out. So, equal to 1 t2 dt prime 1 plus d by dt prime delta t expanded out as a Taylor expansion. So that's first one is L, and I'm expanding out about x dx by dt and t prime. So x dx by dt prime, explicitly writing it, and t prime. That's where you're expanding around. The contribution from the variation in x is equal to plus delta x times partial derivative of the Lagrangian with respect to x. Then there is a contribution from the velocity. So this time I will call this velocity, right? It's for convenience. So that's v. So then I have plus. This whole thing is a variation, right? This multiplied by the partial derivative at L. So this is d by dt prime delta x. That's partial derivative of L with respect to the velocity v. And there's one more term now. Maybe I can write that down here, plus or minus this time, minus dx by dt prime, d by dt prime, delta t, and partial derivative of the Lagrangian with respect to the velocity. And finally, I have plus delta t times partial derivative of Lagrangian with respect to t prime. Is that clear?
Yes. Yeah. That's
Very good. Okay. I have to now expand this out, right? Again, remember I have to keep only the leading order, right? The first variation is the only important thing. If two variations come together, I can drop it because I've already dropped things. So let me rewrite this W plus change in the action. I can multiply this 1 with each one of them. There is 1, 2, 3, 4, 5 terms in here. I can multiply 1 with them, each one of them. But when it comes to multiplying the delta t term, that's already a variation. Right? If I multiply with another variation, that becomes second order. I don't want that. So when it is the delta t variation multiplying, that multiplies only with L. Rest everything I can drop. So with that idea in mind, I collect the terms as T1, T2, T2 prime. And the first one is just L. And this time I don't even write the dependence in there. So I'm multiplying 1 with this. Then I have plus variation in the Lagrangian with respect to x. Then I have this term here, plus d by dt prime delta x partial derivative of L with v. That's done. Then I have this one minus x by dt prime. Maybe write it on that side. D by dt prime delta t. That's velocity, right? But let me write that explicitly. Visible? Yes. So I reached here, that's 1 multiplying this, and finally I have also plus 1 multiplying delta t times partial derivative of L with t prime. And finally, so that's all 1 multiplying the rest of the brackets, but when it comes to the second term in the first square bracket multiplying out, there is only 1 contribution. And that's multiplying with L, because the rest everything is higher orders. Questions?
no questions.
The first term here is the action itself. Right. First term is the action itself. So that goes away. So that allows me to kind of collect things together, except that the variations here don't come up as free variations. So I had to move the derivative out, right? I had to do this uh, integration by parts to uh, release that variation. So I have to process this term here, this term there, and this term there. So I have to switch this variation. So what is the, you write that down. So the variation in the action, that's what we are interested in, is equal to so that is T1, T2, T2 prime, collect. This is a clean variation that's available, but the only one, no, so these two are the clean variations, right? Rest everything I have to integrate by parts. So integration by parts gives me this is, or writing this if you want as a total derivative dt prime of delta x times dl dv. That's this expression, but that's not completely correct. So I have to take a negative, right? So this is delta x times d by dt of partial derivative of the Lagrangian with velocity. So that takes care of these two expressions. Let's do the same thing with this, but before that, maybe I can squeeze this in here because I'll need space. Write this down. So that's delta t by t prime. So that's taken care of. So I have two terms remaining. Both have, I need to release these variations in time there. So I'll integrate by parts again. Or the idea is to integrate by parts. So that's not done there. Okay. So that's equal to, so this one will be minus d by dt prime delta t dx by dt prime. And then there's dl by dt. So that's this term, but I have to make it correct by hitting d times d by dt prime times let's say dx okay, so that takes care of this. And finally, I have one more term there. Hopefully I can squeeze this in. Cos d by dt prime delta t l minus delta t times l by dt prime. Are you with me?
Yes, you used integration by parts 3 times, or was it just?
That's correct.
Just
Once, twice, thrice.
okay. Yeah. Okay.
Basically, to release the variations that were coming inside variables. Okay, so now if I were to put this all together, so I'm going to put this all together on the other side of the board, let's say. So this reads, I change an action is equal to this T1, T2, dt prime. Or let me write this as three integrals. So first, let me write this, anything that has a delta x. Right, I collect them. The first term has it, and anything that has a delta x in the free form. There are two terms that are there, and that's the following. So this is dl by dx and minus of d by dt of dl by dv. And that should be a reminder, so that should ring a bell, right? So that's your usual, if there was no time dependence in the problem, that's what you would have captured, right? That's your Euler-Lagrange equation. But there is more to it, right? Of course, there is much more than that. So the second one is now we collect all the variations with time. Due to the boundary, we have now moved the translations all from the boundary into the Lagrangian. And explicit time dependence comes up in two places, no, three places, I see, right? So I've now done this too. So this has been taken care of. So delta x, two places gone. Delta t now is yeah, I can write it in the following manner, right? So this is equal to, let me write this as delta t, and let me start by curly brackets. This is dl by dt prime. And the other two terms are, interestingly, a total derivative, right? So there is a total derivative, d by dt prime. And let me open a square bracket inside. This is dx by dt, dl by dv, minus of L. So I've written it in a very specific form. And there is some more remaining, but whatever is remaining is a total derivative, which means they get contributions only at the boundary. These are the actual variations in delta x and delta t. This is d by dt prime. And this one is, let me write this as square bracket. So, what are the terms? Again, there is delta x times L by dt. So that's this term, and there is time variation which can be collected as minus delta t times, actually, let me write curly brackets here again. This is curly brackets, but again, this shows up in the same exact manner. So it's minus delta t, notice. So this is dx. Or by the way, this was t prime. Dx by dt prime all times of t primes. L dv minus of L. And that covers everything. Okay, so reorganizing those terms. Okay. Any questions there?
I don't believe so. Thank you. I'm sorry. I do have one question.
Yes.
So that very bottom term, that's the actual endpoint variation.
Yes, exactly. Because these two cancel out, right? Like dt prime, this contributes only at T1 and T2. This whole thing evaluated at T1, this whole thing evaluated at T2.
Mm-hmm.
So even though we made variations at endpoint, there are two kinds of variation that showed up. One actually distributes into the whole global time, right? That's this time. We made a transformation in, or we made a substitution in time. So this is what we captured out of that. So this is completely everywhere there. But this is only at the time, like if you have, for example, what is, think of, move that, oops. So d by dt prime, dt prime of integral of t1 to t2 of f of t prime, let's say. That's the same as dt prime cancel out. So this is a total derivative, right? T1 to T2 df, which is equal to f of t prime evaluated at t prime equal to T2, t prime equal to T1. Is that clear?
Yes. Thank you so much.
This one is like that. But there is a variation contribution coming due to the initial variation in the time at the boundary, which spreads out into the whole path. So if I were to write this now as a differential statement, a functional derivative, so we get change in the action as a function, or because of the variation in x along the whole path, is equal to the Euler-Lagrange equation of by dx minus d by dt L by dv. That's the first line. The first line gives you that. Is that clear how I'm reading that out?
Yes.
Right, that's a functional derivative. But the idea is the same. It's just that's a formal way of writing the functional derivative. There's also the variation in the action due to variation in time, where this variation can depend on t. That's everywhere. This variation as a function of time, that's equal to L by dt prime, dt plus d by dt of minus L. And finally, the last one is the interesting one. This is not the variation at arbitrary point, but you can write this in the following way. So since it is only at the boundary that is showing up, so this is delta L, sorry, change in the action due to the change in X at the boundary. So let me call that as T1 or 2, right? So let me say this is T1. This is applicable for T2 also. That's equal to dL by dV. Maybe I should say this is evaluated at the boundary, right? So let's say this is evaluated at the boundary. Or T equal to T2. And action evaluated at the variation in the action due to time evaluated at the boundary, T1 or T2 again, is equal to X by dt minus L due to variations at equal to T1. But of course, once I have set this T equal to T1, I can release that and call this at every point in time at some time was a boundary, right? Like as you're evolving in time, the present is your boundary. So in that sense, this can be released and this can be returned to be a general expression. Is that clear what I'm stating?
I believe so. As in, like, the boundary will become, not the boundary
Yes,
as it evolves. Yeah.
So if you're going along this time, so if you go from T1 to T2, that's your boundary. But if T2 moves, like if you are moving along T2, if the particle is really moving from T1 to T2, it is actually moving along. So T2 is going around. So like today's T2, today's time is going to become yesterday in a sense, right?
Right.
So that's where we are, right? Now here is where if you want to bring in the physics that when you say stationary action principle, let me put it the following. Let me release this T equal to T1 there and explicitly write this as T equal to T1 so that I have an expression there, except that these two look the same, but now this is a contribution from the boundary. That's from the boundary. Okay. Now here is a stationary action principle. Stationary action principle says that the variation in the position of the particle along the whole path has to be equal to 0. This is dynamical, this is 0. You set this to 0. This is equal to 0. That's stationary action principle. You say that variation in the action is 0 because of the change in path. Same thing with time, this is set to 0. These two are dynamical. Right? That's happening. You're treating the whole path at the same time. But these two are boundaries. That's not 0. But instead, this is used for defining your quantity. What is dL by dV? Does it ring a bell? We have seen this before. We have defined this to be something.
Is that like the canonical momentum?
You said this is defined to be P. That's your canonical momentum. So the variation on the boundary is used to define your momentum. So momentum shows up at the boundary at every moment, and because one time always is at the boundary. And what is the second term? Does that ring a bell?
I, I think it might like the canonical force. I think
No, this is momentum, right? P.
P. Yeah,
And that's velocity.
velocity. Yeah. Oh, mv
Velocity
squared.
P minus L. That's a Hamiltonian.
Oh yes, yes, I see.
That's a Hamiltonian. Right, so everything fits in together now. And let me actually go back and write, this is the same. So actually I can do one more thing here. Yeah. So now that I have defined these quantities, I can rewrite this equation as dl dp by dt, which is a force, is equal to dl by dx, right? That's your Euler-Lagrange equation. Same thing here, since this is the Hamiltonian now, it says, where is this in some space? So this equation states that dh by dt is equal to minus dl by dt. The total derivative of the Hamiltonian with time is actually negative of the partial derivative of the Lagrangian with time. So that's your equations of motion. These two are equations of motion. And these two are definitions of momentum and Hamiltonian. Okay, let me do one more step and start. So this is mostly we have, now we can start using understanding the symmetry principle from here. But let me put this all, let me put the boundary terms more clearly here. So let's say I say that since if we are talking about the particle itself, after invoking or using stationary action principle, remember stationary action principle sets the variations along the whole path to be zero. Once I do that, my change in action, there's still some variation in the action though, right? So there is a variation in the action reduces to completely on the boundary. So that's T1, T2, dt prime if you want. I can even say as t, right? So dt, d by dt. And there are two terms. One is delta x. And this was dl by dv, but that is t, right? That's t. And the second term had a time to it, that's delta t, which is basically the Hamiltonian. If I were to upgrade this to 3 dimensions, this will become, so this is now 3 dimensions. So let's say this is 3 dimensions. It's straightforward. It looks exactly the same, T1 to T2, T. There will be 3 positions, 3 momentums, and the time is the same. So this becomes a dot product. Dotted with P minus of delta T of H. Okay, and where P now is, maybe I should clarify this since I introduced a new thing. So P now is partial derivative of L with respect to velocity, V as a vector, and H is now the Hamiltonian, which is velocity dotted with P, where P is this dl by dv minus the Lagrangian. One should see the structure of this negative sign. That is relativity inbuilt in there, right? Remember that in relativity, your dot product shows up in space has your positive part and the time has negative part, or it depends on the convention, which one is positive and which one is negative. So that comes out inbuilt in here. So this is it's like a Fourier transform, right? Kx plus omega t, right? So you would say this is equivalent to Kx minus omega t. So omega has this energy feature in there. So that's the idea in there. And what I'm going to do next is talk about, and remember this is at the boundary, right? The way it is written, this is at the boundary. And try to talk about what happens if you make things, how do we see the symmetry and conservation principle showing up in this experiment. So this is where we want to investigate these 2 lines for symmetry or the noises field. Okay, is that clear?
Yes, it is clear. I have a quick question. So we use the stationary action principle in order to make the variation at the endpoints equal to 0?
No, not at the endpoints. Notice, okay, we'll go back. So yeah, so this were your 3 terms, right?
Yeah.
Delta x, delta t, and this is the boundary, right?
Oh, well, yes, yeah.
But now you say that, and you say that stationary action principle is used to set the first and second to 0. That's the first and second, right? That's first, second, and third one. I've written it in two different ways, right? Two terms there. First and second depend on the whole path. That is zero. That's stationary action principle. When I set this to zero, that's stationary action principle. That is not necessarily zero, right? But you say that it is zero because that's your equation of motion. That's Newton's law. So you say that Newton's law requires that this be zero. That's stationary action principle. Similarly, this is not Newton's law, but this is conservation of energy if you want. And that's also you say is zero because you invoke that as a stationary action principle. So these two are coming from stationary action principle, and whatever is remaining is these two then. That's the boundary that is remaining. Is that clear?
Yes, yeah, no, I got it backwards. I definitely see it now, yeah.
And then what is left out is this then.
Right, and that is simply due to the boundary.
Boundary, exactly.
Yeah. You called the delta W, you called that something and I forgot to write it down.
Variation in the action?
Variation in the action, yeah, that's what it was.
Variation in the action after the equations of motion have been used or the stationary action principle has been invoked.
Okay.
Okay. So let me stop here and we'll come back and start from here next time. Okay.
Okay, that sounds good. Will you be available at all tomorrow? I know tomorrow's usually busy, but.
Yes, tomorrow I have office hours, which I have it on Zoom, but if you really want, I can come over here.
It's during 3 o'clock, I think, right?
Oh, 3 o'clock, yes, I'm available. 3 to 4, I'm available. 4 o'clock, we have this seminar.
Oh, that's right, yeah. Yeah,
So,
because like I have a meeting with my group tomorrow around 10.
okay, perfect. So then I teach until 3, so maybe I'll be late by a few minutes. But at 3, 3 to 4, I'll be in my office.
Okay. Okay, yeah, that'll work for me.
Sounds good.
Yeah, I'll just stop by then, and I'm gonna review these notes again, and I might have some questions, which is why. So it's just.
Okay.
All right. Thank you so much.
You can. Bye.
All right. Goodbye.